Hello world, we are live and we are trying to solve some LeetCode problems starting with the easy one, which is easy but looks something that a little bit unusual for me. And I want to try to solve it live. 1, 2, 1, 2. Yeah, looks like there is sound. So I'm sharing that one. And I also have a medium level one. But let's see what we can do with this one within 30 minutes. It's supposed to be an easy one, so it should be like 20, but we'll see. So what we have, convert sorted array to binary search tree. Binary search tree, BST, okay? And we given an integer array nums where the elements are sorted in ascending order. Array, convert it to a height balanced binary search tree. Height balanced binary search tree is a binary tree in which the depth of the two subtrees of every node never differs by more than 1. Okay, so the heights, and basically it's sort of, how many nodes are there? 10 to 4 nodes. It's sorted in strictly increasing order. So I think the easiest case would be to just do split it in the middle. Could it be? Could it be? Could it work? So let's look at the examples. Input these numbers. Output is a tree. And in binary search tree, all the nodes to the left are smaller of every, all the subtree of every node, to the left is smaller. But I mean, we can even look at this children. So the left children is smaller than the right children. The left child is smaller, the right child is bigger, and that actually applies to all the children to the left, or the descendants. Yeah, but I mean, if you do this traversal where you go from left, then you go to node and turn to the right, which is called post order, I think. Post order traversal binary tree. Post order is, you go left node. Oh no. Wait a second. It's not post order. It's not. So I think we need to look at tree traversals. In order is goes from node. In order goes from left node right. So it looks like in order should be always. I'm thinking. I'm looking at left node right. Yeah, should be in increasing order. So I mean, left node, right, left node, node, left, node, right. So, well, let's say it's in order. It doesn't matter. What matters is it's it's called it doesn't tree traversal. Um, yeah, it looks like it's um, left node right is in order. Yeah, so basically it's left node right. Yeah, I think it's yeah that way. That way we'll get uh, mm, mhm. And by the way, do we need mhm. Yeah, so why I this problem looks a little bit conventional to me, and that's why I picked it. I want to get used to some problems that are not that I'm not used to. Yeah, which is um, because I'm pretty comfortable with tree traversal, um, but now I have to convert this uh, into a tree. So how would I do that? So if we go from the first value, we'll look at it and we create a node. We do need to create a node, right? So we do need to say that there is a node, okay, and that node is a new tree node, okay, and now we need to say that this node val is this nums I, yeah, and what do we need? Yeah, what do we do from there? hmm If we just start, yeah, if we start from the left, or we could just start. hmm hmm There is at least one node. I'm thinking this. Why don't we start in the middle, somewhere in the middle, and then just connect, like uh, we'll have this connect all the nodes to it. Yeah, we'll have this mid, which is length of nums divided by 2. So, and we'll start from the middle. We'll take the left, and yeah, we'll have left will be mid, and right will be mid. Yeah, left and both will be mid. And for what we'll be doing, we'll say, let's say for left is more or equal 0. So as long as both and r is less than the length of nums, yeah, we'll take the we'll take the we'll start, yeah, we'll take that node and start connecting. So, so we'll say, I mean, but here is the thing, we will need to move. So what we want to do, well, let's say we start with 0, create a node, and move our pointer to the left, then move our pointer right to the right, then we'll connect both of these to the 0, and we'll, yeah, the left tree will move the nodes also to the left and to the right, and then we can just continue doing so till the end. We'll pretty much have just 2 branches. We could do that, right? That will create us a tree of this height, and should be balanced because we started in the middle. Okay. Oh, I forgot to run, but it's okay. We have the timer here, so. I mean, it's going to be higher than, but it might not be the best because it's pretty much just sort of like 2 linked lists. Yeah, by the way, what we can do is just build those 2 trees to the left and to the right, and just connect them. Yeah. If we wanted to do it more, wait a second, height balanced, in which depth of the 2 subtrees of every node never differs. Oh, okay. That means we cannot do every node. Yeah, for this node, also the subtree, yeah, it has to be height balanced. So we cannot do that. We need to still start in the middle and start building those subtrees. But the thing is, those subtrees also need to start in the middle. Yeah. So that's a repeating task. Hmm. I see. Yeah, so it looks like, well, our repeating task will be, hmm hmm and in typically the binary search starts with them in the middle, then it move it to the left, move it to the, in this case, yeah, you divide it. In this case, we'll need to divide it. Just divide, uh, hmm, 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 hmm. Interesting. I mean, but how many pointers do we need? Yeah, 15 minutes into, yeah, this like this reverse thinking about, yeah, this converting is definitely a little bit different for me. But but that's the point of today's exercise. That's the point. That's what we want. So let's see how many. I mean, how do we want to do that? Yeah, we will need to create it, but we need to divide them every time. So mm, that's a repeating exercise. Yeah, let's look at the picture. So we divide it in half once, but this node is going to come from the middle of the left half. And this node will going to come from the middle of its left half. This one from the middle of its right till. So it sounds like a bunch of ranges, and sounds a bit recursive. So we want to pass, but we need to take care of both. So like this, do we? We look at the left, get its node. Look at the right, get a node. Then, well, let me put it that way. Let's just think about this as the source for the values. Okay? Let's think how we will, if we are to build a binary tree, which we are to do, height balanced. How do we want to build it? Do we want to do it depth first search? Do we want to build it breadth first search? Because it seems like it's going to be something like that. Yeah. And then while we're doing that, we will also extract the values for that new tree we are building. So nobody's going to build that tree for us. We need to do it. That's kind of my thought. Yeah, one way to think about it is I think, and let's see if we can do it with DFS. Which will, yeah, DFS. Because you see, we don't have that tree. I mean, if we simplify the problem, like we already have the tree, just fill it up with the values from this array. All right, so then we will do the DFS. In this case, we just don't have the tree yet, but we still need to, we also need to build it and we go over it. So the DFS function is going to be a function which going to take a node of type tree node. Might not return anything. Let's start like that. And we'll say the DFS is. And yeah, so if we were to build it in order, then we would just go over the array from left to right. But I'm not sure we can know exactly how many nodes we need to build. And before we fill them up. By the way, it's not the worst idea to also consider doing it in 2 steps. One, to build the tree, and then to fill it up with values. Because we know how many nodes we need in total. And yeah, then we would just go in order, left node right. Yeah, we'll go in order and just fill it up while taking values from the array. So we are traversing 2 things here. One is array, and another is this tree, which we need to build. Question. Do we want to build the tree before filling it up with values? Can we know how many, because we know how many nodes we need, right? So we can probably just build the tree of the needed height. But look, it's a problem on its own. Yeah, that's why, like, intuitively, I did not feel that this is an easy level problem, unless it has like 5 lines. It's a 5-line solution where you like sort of do this binary recursion in the array, and then just plug the new nodes. But the building a new tree is building a new tree is a problem, is an easy problem, but a problem of itself. So, I mean, if we do DFS, or be a breadth first search, we would be able to know, like, to get the needed number of nodes. And stop at the node. Yeah, it will be height balanced, right? But We can track the number of nodes automatically along the way. But I mean, to do it with the DFS, we would need to calculate the height. But it's this last row is it's going to be different. So that's why it's not going to be so the problem of just building a height balanced tree using DFS of a certain number of elements doesn't look like an easy problem for me. Well, it's at least from what I'm from into that's what's confusing me a little. It says easy level, but if we do BFS, BFS is not that easy by itself. Breadth first search, but breadth first search will allow us to build level by level and stop exactly at the number of the last node that we the last node at the right amount of nodes that we need, and it will be balanced. Should be balanced. I feel like it should be balanced. Yeah, but that will be breadth first search, and I think it will take another. The sub problem then will be to fill it up with values, because sourcing values from the array level by level is a sub problem of itself. Easy level or not easy even. So I'm not seeing. I mean, I'm trying to look at this 5-line solution. Like, okay, you just need to do like this. I don't know, this recursive call on the array, and if we do those. And by the way, here is what I'm seeing. If we use DFS, it will be in order, and then our array will be from left to we can from left to right. Source data will come from array left to right. If we do BFS, if we build, by the way, building, but DFS to build is, if we try to build it in order, left to right, where do you stop? Well, we can we can calculate the height. We can calculate the height and then stop at the last node. So it'll be like left to right. So many things to choose. It's a problem of its own. Yeah. Building using DFS in order. Left node. In order left node right. Yeah. Filling it up with data. Yeah. So that will be writing data. Yeah. writing data in order. Yeah, we'll need to read data from array like that. Yeah, but if we do BFS, then we can build it, but then we will need to build. We can build and write, but we will need to read from array with this some kind of recursive binary sort of, not the binary search, but splitting. Yeah, sort of binary search. Yeah. Yeah, that's why I'm not seeing this as an easy level problem, at least for now. Right now, is there editorial? No. Okay. Okay. One thing to notice now. One thing to note is if this is like a warm-up level problem, it's not really, at least from what I see. Or I need to practice with these conversions from array. And the fact that array is sorted, yeah, we will need to sort it otherwise. Yes, anyways, it looks like I say we need to use both. Yeah, to build, we should use BFS, but to write values, we should use in order DFS. Yeah. Because, yeah, building it with DFS, in order, you need to track the depth. Track, yeah, the total number and the depth. Yeah, like you went. And yeah, you can calculate the maximum depth you need. But again, I mean, that's the maximum length, but you don't know how many nodes you need on that last row. And you can calculate it, yeah, how many nodes you need on this last row. But it's just easier to do it in BFS. You don't have to, yeah. But I mean, I think it's easier to do it with BFS, to build it and then fill it up with DFS. But it's like not an easy problem. It's almost too it's strong medium level problem. I wonder, well, 34 minutes. I think I should look at the hints or topics at least. So topics, divide and conquer, binary search tree, binary tree. Oh, yeah. Oh, by the way, there's no hints. Yeah, divide and conquer is what I was thinking. But can we just do it like, yeah, just divide into halves. like divide this array and pass it. Divide this array and pass it. So, I mean, if we have 3 values, and if we can extract through that, can we build a node? Yeah, so this could be sort of a depth first search. Yeah, solution. Yeah, I'm thinking if we have 3 nodes, just 1, 2, and 3. Can we build yeah, well, what we need to do is look at the middle, and we build our tree for and I think when do we stop? I don't know. I'll think about it, but let's just, yeah, we have this for loop. We start with the middle of and we will have it's actually we might not do it in a for loop. We might do it in a can we do it in for loop? Yeah, let's abstract away that. So we have this middle, we create the node, okay, and in the middle, okay, we created first node. How about that? Then we need to do the same thing on the left side. Yeah. And by the way, when we call it, we need to pass the new. When you'll have our left and right, the indexes, yeah. I don't know, yeah, what's the base case, but it seems like so. And okay, so we started TFS. We'll start with by the way, there is no node. We're not passing any nodes here. We're just passing the range to work with. So we're passing 0 and length of nums -1. And yeah, we have it. we have the node 40 minutes into. Okay. Yeah, but look, we already have our node. At least we got that. And by the way, we need to return this first node. So we kind of need to remember somehow this initial node. So I guess we need to create a root. By the way, if we want to create a root, probably need to pass some kind of node, yeah, into our calls. So node. Because, so we do need to create a root. Yeah, root is new node, and we're gonna pass it to it, yeah. And well, then we're not creating the root. We will create its field, so we have the root. So we'll need to create its children. Mm-hmm. Mm-hmm. The root is being passed. Right? Right. Root is a new node. We're passing it. Yeah, okay, so I'll figure it out, but why are we creating a new node here then? We'll see if we need to do that. Okay, so at least we have the node. We know, yeah, we put its value to it. Okay, now we need to create the left node and the right node and pass them to the left and to the right. So we'll call DFS. Where do we connect them? We'll say that node left is this node right is DFS of this. So what will happen in this call? What first will happen is this call for this DFS call before this assignment. So we'll get all the down to the bottom. Yeah, we don't know where we need to. Yeah, we'll set up the base case where we stop. So DFS, and then we pass the new range. For the left, it will be left, and instead of right, we'll have the mid. Right, mid minus 1, because we don't need to do the value itself. Yeah. Here we'll have mid plus 1 and right. Yeah. And we don't need to do the call if we only need to do this if left is less than 0 or r is more than or equal than length of nums. We're done. Yeah, I didn't need to do anything. So we did the DFS and return root. So it could be that we actually have it expected new line and argument. Okay, but so let's test it. Yeah. So I have the root. We have the DFS function. What it does, it gets a node and a range. If we are within the range, if we are outside the range, if left or right, so we don't need to do anything. We just return. But if we are within the range, we figure out the mid, and we assign that value to that node, and then we do several magical things. Yeah, so we need to then we could assign what's the left and right. We want to do that, but where do we get the left? We call new DFS we create a new node and pass it to it. Okay, so the new DFS goes and we pass the new range. That will be the range from the left to the middle. Yeah, so that was without the middle. So left and right will be both here. And right will call here. And middle will be on those. And those will create them. Well, those will assign. That assigns the value. Tries to call it again, gets, those become, oops, I forgot something. We need to return the node. Yeah, so we need to return nil if, and in this case, we return tree node. Yeah, tree node. And once we're done, at the last nodes, return node. Basically, you got that node from your parent. You just fill its value. That's what this one will do. For one, it will get the node, fill its value, not create any. Well, it will create new nodes, but it will create new nodes, but it will not link them. The DFS will return nil eventually. Yeah. The DFS will return nil. Oh, wait a second. I don't get it. This is like, oh, new node here. Yeah. So we create, yeah. And the reason we have them, yeah, we do it that way. We create the root. Define, oh, new needs to go like, oops, the keyword new. Oh, it looks like we never stopped. Okay, so if either of them is outside the range, yeah, so in our test case, by the way, it's more typical to create the node inside the call. Yeah, it would be more, but to create a node inside call. But how do we, if the first root node will be created inside the first call, yeah, how do we keep track of it outside this call stack, this whole thing? So it's kind of easier just to do it like that. Yes, the new struct will be created, but okay, so let's test it. Let's okay, if left, so middle between 0 and 2. Oh, yeah, obviously, yeah. Well, it's not the length. The middle, how do you calculate the length here? The middle is, um, it's left plus right. No, it's not like that. Yeah, no. It's right minus left. Yeah, if you do binary searches like regularly, it's just it's a pretty trivial calculation. Mm, this yeah, but I mean, I think. So what's the middle? Like, take that test case. Well, basically, if you just take 1, 2, 3, 4, 5, the middle, yeah, if we just take 5 minus 1 is 4. And then we divide 4 by 2. And we get that. So it's actually a little different, yeah. It's like to calculate. What's our timing? 55. 3. Like 5 minus 3 is 2. Oh, I think there is like plus 1 or something. Here, yeah. 5 minus 3 is 2. But we don't want to go into. Yeah, so basically the left one is kind of our I think it's like that. Yeah. Then we divide that difference. It's closer like that. Yeah, this left, which is like 1 initially. Which is 1. And then this difference divided by, so which is 2. So right minus left is 4. And this 1 plus 2 is 3. So that will give us the point. But if we want to go like between 3 and 4, yeah, we'll have 3 as on the left. And we'll have we'll have 5 minus 3 is 2. So 3 plus 1, yeah. Sorry. It's a bit a little chilly in this room. So I do need to practice binary searches more, but this seems to be more correct. Binary search. Binary search. Let me check the trivial binary search to see how mid is calculated. Yeah, this low. Yeah, that's how mid is calculated. Yeah. Then, okay, what are we missing still? Because what we're getting is, looks like we're just running out of memory. Creating too many nodes, I feel like. Yeah, because, I mean, in this case, we take the middle node, assign its value. Oh, the middle value, assign it to our node. Then we start, go to the depth. Make another call where we say, okay, now it's left side excluding the mid itself. So now it's only these two. Only these two, which will be 1 and 2. So it will be 1 by 2 is 0. So it will be like Oh, it's the trivial is binary search. Yeah. Mm, yeah, when you do it like that, well, high moved to the left, low, mid plus one. Well, yeah, the new low becomes new high, mid. Yeah, mid is moved because we have already taken it. So we are, yeah, I mean, we don't need the mid anymore. We already took its value. So the new right is gonna be mid minus one. So it's gonna be this. And so, I mean, overall, this call timing 1 hour. Yeah, gotcha. Um, yeah, I mean, that's what I thought. It's this easy problem that you need to take an hour to solve. But I think we're pretty close. Um, so overall, this call will assign the value and then do recursive calls, but it will stop. I mean, this call will be waiting on the stack. So, like, is this zero is created, this middle zero node is created, and it's waiting. So it calls on the left, and on the left it will come with, it should come with this left and right, and they're actually like that, but that doesn't matter. Should not matter. So we'll give you the 0 and 1, and okay, left is 0. All right, 1 minus is 1. And so that will be 0 plus 1 minus 0 is 1. 1 by 2 is 0. Integer 0, yeah, so it will be 0. So the left one, for some reason, will be connected to this one. The right one, yeah, but before it does, it will, so then the mid will be the new mid. So this one will have left still. We'll call the left again. Mid will be 0, left is 0. Left is not smaller. Yeah, I think these ranges are a little bit off because I don't think we ever get out of this because our left is limited and our right is limited. And I'm not sure the mid is calculated. Although, I mean, it's kind of natural that we will only take this, right? But we might want to shift it a bit, the mid, the way we calculate the mid, and take the right one. Yes, sometimes you need the mid to be shifted. If we not do that, will it work? Because I feel like, no, we're still. If we shift the mid, because we need to do something to yeah, we do need it in the middle. That will give us right minus left. So it will start right is it will be 4, 2, so we'll get that. But then we're looking at these, and we need to get the middle of those. But what if there's two? If there's two of those, it gives us the left one. And then I think it's just we hit a like this never-ending loop of zero value will be just created and created and created with right, because look, left is always L in each call on the left side, and the middle is calculated, never goes out of range. And I think we never even hit that one, this index 1, this case, which we should. Right? Or do we? Because, I mean, yeah, when we have that range, so the new left and right is 0 and 1. Middle is calculated as 0, right? Because 0, yeah, we did, like, right. 1 minus 0 is 1, and at 0, yeah, so the mid is here. And it calls left. And it calls left again with left and 0, so 0, 0. And that 0, 0 we need to do we? If they are the same, left and right, if they are typically in a binary search, well, you still can, yeah, you still need to take care of the node. Yeah, so I think we're pretty close, yeah, since we are an hour into it already, an hour and 8 minutes. I would say one of the takeaways is to play around more with the binary search, because that's kind of the sub problem here. The binary search, yeah, or divide and conquer with these pointers, because it looks like, yeah, the left one just loops, it always returns middle 0, and then when mid is 0, it's just wait a second, when mid is 0, no, mid is 0, it becomes -1, so it does not go to the next call. So actually, yeah, so when mid is 0, it signs that, but it goes and doesn't, it returns nil, the left one. So meaning it will attach this -10, Wait a second. The left, we need to return it. Yeah, well, it will create a node and it will assign -10 to it, right? Right. The left one mid will be 0. Yeah, so -10 will be that -10 will try to create a left node, but it will not. So it will try to create a right node, which will be this one. Oh, which will be mid, which is 0 plus 1. And the right of it, the right was 1. So the right will get like 1 plus 0. So the -10 should be here. So it will be 1. Left will be 1 plus 0. So mid will be 1. Then that one we'll call left again. What will be the left one? And this one, it will be, it will be already 1, 1. It will be left one, will be 1, then 0. Oh, yeah. I think we need to and left bigger equal around. Yeah, maybe that one. Another requirement. Yeah. So at least, yeah, we stopped running out of memory. But so it looks like it never gets the -3. Yeah, so it does hit us the -10 is there. -10 is there. Then it goes this -10. Yeah, doesn't find the right one, but -10 had a call of 0, 1. And the mid for -10 became 0, so it will be -10 will call 1, and right was 1. So here, when it calls it, it should get 1. Wait a second, since it never connects anything, it looks like it drops out. As long as right. Oh my goodness. Is less than length. Oof. Now we're 0. Well, wait a second. As long as right. Oh, wait a second. No. If left goes out, if out of 0, yeah, we're done. If right goes over the length, we're done. Or if left is bigger than right, yeah, Yeah, I forgot the logic. Finally. Fine. Finally, some honest. Wow. This is an easy level problem. Look at that, my dear viewers. Yeah, I would say, yeah, the key takeaway is practice divide and conquer, practice binary search. Because if you practice those, yeah, those binary searches, you will get more comfortable with these pointers, definitely. With these pointers and the conditions. Yeah. But what I like about it, besides the fact that we did solve it within 2 hours, now it's not just two, it's just an hour and something, an hour and 15 minutes. Yeah. But like time, 15 minutes. Um, is that what I like about it is that we found this how to remember that first root, because if we try to create one root in each call and then return it, I mean, how can we do that? Because we need to keep that. Oh, oh. I think we could. I think we could. So, I think we could, and this is how we would do it. The thing is, our node, our DFS returns something, and it's that node. It's that node. So we could call it without, we don't have to pass anything into the call. We don't have to pass anything into the call. We create that node in the call if we need to, only if we need to, yeah. And yeah, so each call, if needed, will create a node, calculate the value, assigns it's the right value, assigns their value to that node, to the recursive calls. Yeah, so we go to the depth. Once we build, yeah, and at the end it will return, yeah, it will return either nil or it will return a node finally. Yeah, when those like two nils are returned, uh, the node is returned, yeah. So it should be work as well. Yay! This is probably the nice and short way to do it, yeah. Yeah. Yeah, we'll create a new node. Yeah, we do need that node here. All right. 120. Good time. Good solution. Good problem, good solution solved. In 120, 115. Yeah. It's a combination of binary search and DFS. And I like how strong that easy level problem is. So that's our first practice for today. Thank you for watching. Like and subscribe, and we'll see you in the next video.